Hi everyone, I am Nicole B. Bureros, an NDU graduate under Accountancy Business and Management and currently pursuing Bachelor of Science in Accountancy. I'm the first reporter of Group 2 and we are tasked to report linear programming, computer solutions, and sensitivity analysis. To start off, the application of management science techniques has been frequently credited with increasing the efficiency and productivity of business firms. It has been very helpful in solving problems that confront manager and decision-making processes by developing mathematical models. Now, in the previous chapter, we learned how the linear programming model is being formulated and how it can be solved through a graph representation of the model. This method works almost all different types of problems but gets more difficult to solve when the number of decision variables and constraints increases. So this is where latest technological advances kicks in. The application of mathematical model and computing technology merges to help decision makers solve problems. We will also describe how to use a computed solution result to experiment with a linear programming model to see what effect parameter changes the optimal solution referred to as sensitivity analysis. Now let's get started with our first topic for Chapter 3, Computer Solution. In 1940s, linear programming was first developed. However, during that time, the technologies or inventions are not yet capable to perform these complex problems. They use what we call simplex method, which is a lengthy manual mathematical solution procedure. After 6 decades, computer technology improved and evolved in which it was more used to solve linear programming models. The mathematical steps of the simplex method were simply programmed in pre-written software packages designed for the solution of linear programming problems. It is easy to use and less costly. That's why it was expanded and used by businesses today. Now, simplex method has become less of a focus in teaching of linear programming. However, simplex method is useful in gaining overall understanding of linear programming. As noted, computer solution itself is based on simplex method. Now let me present my PowerPoint presentation about Excel spreadsheets. Before we begin our discussion with Excel spreadsheets, please be informed that Chapter 3 is exclusively focused on computer solution. Also, if you want, you can also bring out your laptops for you to be able to follow the processes in solving linear programming problems. Once again, good day to everyone. Now, let's first tackle what is Excel spreadsheets. Let's start with what Excel spreadsheet is. Excel can be used to solve linear programming problems, although the data input requirements can be more time-consuming and tedious than with a software package like QM for Windows that is specifically designed for the purpose. However, once you already set up one problem in spreadsheet, you can use it as a template for other problems. Next is when you are reporting and presenting. A spreadsheet is a very great way for you to be able to present the problem and its solution in an attractive format. And lastly, a spreadsheet requires that column and row headings for the specific model to be set up and that constraint and objective function formulas be input in their entirety. And now, let's start to set up our Excel spreadsheet. Let's use Beaver Creek Pottery Company example, which was introduced in Chapter 2. Okay, first let's input the data which was also shown in Exhibit 3.1 in our material. The values for bowls and mugs are contained in cells B10 and B11. And for our profit, it is in B12, cell B12. These cells are currently empty or zero because the model has not yet been solved. Okay? The objective function for profit is C4, type it, type equals, and then click the cell C4, and then multiply in Excel spreadsheet. Asterisk is used instead of X. Then click cell B10, then add, then click cell D4, and then multiplied by cell B11. This objective function is embedded in cell B12 shown in the bar or in the formula bar. This formula is essentially the same as z is equal to 4x sub 1 plus 50x sub 2, which was shown in chapter 2 by the group 1. Here, the B10 and B11 represent x sub 1 and x sub 2, while B12 represent z or the profit. Next, the objective function coefficients 40 and 50 are in the cells C4 and D4. Similar formulas for the constraints for labor and clay are embedded in cells E6 and E7. Let's look for E6. In E6, we put the formula equals C6 multiplied by, then click B10 plus, then click cell D6 multiplied, then click B11. So our formula is C6 multiplied by B10 plus D6 multiplied by B11. Now, in E7, we put the formula C7 multiplied by the cell B10. Let's click the B10. Then add D7 multiplied by cell B11. So our formula in E7 is C7 multiplied by B10 plus D7 multiplied by B11. Here, under the constraint, the lesser than or equal to sign in cells F6 and F7 under constraint are for cosmetic purposes only, meaning they have no real effect. In H7 or leftover, under the leftover heading, the formula we input is equals to G7 minus E7, and in H6 we input G6 minus E6. To solve this problem, first click on the Data tab on the toolbar at the top of the screen, and then click on Solver on the far right side of the Data toolbar. If you can't find it, you can always use the search bar. The Windows Solver parameters will appear as shown in Exhibit 3.2 in our material. Initially, all the windows on this screen are blank, and we must input the objective function cell, the cells presenting the decision variables, and the cells that make up the model constraints. Now, when inputting the solver parameters, we first set objective, which is, in this case, B12 for example, since our profit is embedded in cell B12. Next, we indicate that we want to maximize the objective by clicking on Max. We achieve our objective by changing cells B10 and B11, which represent our model decision variable. It means that all the cells between B10 and B11 are inclusive. Next, we input our model constraints by clicking on Add, which will access the screen to another command just like what is shown in Exhibit 3.3 in our material. The cell E6 contains the constraint formula for labor, whereas cell G6 contains the labor hours available. We continue to add constraints until the model is complete. So E6, then here we put G6 and click on Add, then E7, then G7. Because E6 is to E7, lesser than is equal to G6 is to G7, which means that the constraints in cells E6 and E7 are less than or equal to the values in cells G6 and G7 respectively. It is also not necessary to put or to input the non-negativity constraints for our decision variables. B10 is to B11 is greater or equal to 0. This can be done in the solver parameters screen, Exhibit 3.2 or Exhibit 3.2. Now, let's click on OK on the Add Constraint window after all constraints have been added. This will return us to the solver parameters screen. On the solver parameters screen, check this where it says Make Unconstrained Variables Non-Negative, and let's select this where it says Select a Solving Method. And then we select Simplex LP. This will ensure that the solver uses simplex procedure to solve the model and not some other numeric method. Once the complete model is input, click on Solve at the bottom of the solver parameters screen. First, a screen will appear titled Solver Results, which will provide you with the opportunity to select the reports you want. And then when you click on OK, the solution screen shown in Exhibit 3.44 will appear. If there had been any extra or slack left over for labor or clay, it would have been it would have appeared in column H on our spreadsheet under the heading left over. In this case, there are no slack resources left over.